Alright, in this video today we're going to recap some of the things that we learned about the new model of the atom, and we're going to extend that a little bit into something called orbital diagrams as well. So if you've missed these classes, you want to take good notes as you go here. If this is a review for you, follow along, and then when you see the new material, begin to take good notes there. So we looked at the new model, the quantum model of the atom, which replaces the Bohr model last week. We know that electrons in the new model are still arranged in principal energy levels. The principal energy levels in the new model are just like those in the Bohr model. Okay, so the principal energy levels. They have designations using the letter n that go from n equals 1 to 2 to 3, etc., all the way up to n equals infinity. However, in the new model of the atom that's replaced the Bohr model, we now have a new complication. The new model says that the electrons are also arranged in sublevels. Now, sometimes those are referred to as shells and subshells. And then within each sublevel, the electrons are found in orbitals of different shapes. The idea of an orbital is what has replaced the idea of orbits in the Bohr model. In this picture, you can see the different energy levels. So on energy level 1, we have the 1s sublevel, and that's the only sublevel that's there. The orbital in the 1s sublevel is called the 1s orbital, and as you can see in the picture, it looks like a small sphere. So what that means is that an electron that's flying around in the 1s orbital flies around the nucleus in a spherical region of space. When you get to the second energy level in the new model of the atom, there are now two sublevels. There's a 2s sublevel with spherical orbital in it, and now there's a 2p sublevel, and the 2p sublevel has what look like figure 8 or dumbbell or peanut-shaped orbitals within it. Level 3, energy level 3, has three different sublevels. So now we have the 3s, the 3p, and for the first time now we're seeing the 3d sublevel. So on energy level 3, the 3s orbital is simply another larger, more energetic spherical region of space, as what is larger than that which was on level 2 and larger than that which was on level 1. There's now also a 3p sublevel, which is larger than the 2p sublevel that was on level 2. So electrons in the 3p sublevel have more energy than they did in the 2p sublevel, so they can fly further from the nucleus, but they still occupy that peanut-shaped region of space. And then now we have the 3d sublevel, which looks even stranger. It looks sort of like a four-leaf clover, this orbital, and we'll see in a minute that there's a further complication that each of the different sublevels has different numbers of orbitals within them. We'll see that on the next slide. On energy level 4, there's 4 sublevels, 4s, 4p, 4d, and now for the first time we see 4f. The 4f sublevels contain orbitals whose shapes are getting really hard to describe. On energy level 5, 6, and 7, we just get more sublevels. On level 5, there's a 5g that's added. On level 6, there's a 6h, and on level 7, there's a 7i. So you'll notice that once you've reached the f sublevel, after that, they become alphabetical in their designations, so 5G, 6H, and 7I. For all of the elements on the periodic table in their ground states, we can get by using only S, P, D, and F sublevels. This slide is showing us the different shapes for the sublevels. On the 1s sublevel, we have a spherical shaped region like we see here in red. Remember, the nucleus of the atom is found at the center of that sphere. And so an electron flying around the nucleus in this region of space would be in a 1s orbital. The 2s orbital is simply the same shape but larger. So imagine this small sphere encompassed within a larger spherical region of space, and now you can imagine a 2s orbital surrounding the 1s orbital. A 3s orbital is simply going to be larger than that again. So 1s is the 1s orbital on energy level 1, 2s is on energy level 2, and 3s is on energy level 3. But notice that on each energy level, there's only one s orbital. So on level 1, there's one 1s orbital. On level 2, there's one 2s orbital. On level 3, there's one 3s orbital, etc. In fact, on every energy level, there's only one s orbital. The p orbitals, however, come in groups of 3. So p orbitals on every energy level where they exist, starting on level 2, there was 2p, on level 3, 3p, on level 4, 4p, etc. There's always going to be 3 p orbitals on each of those energy levels. Notice that they have that dumbbell or peanut shape, and they are oriented perpendicular to each other. In this picture, you see them side by side, but in reality, they would be on the same set of axes. So one of them is on the x-axis, one of them is on the z-axis, and one of them is located on the y-axis. So they're perpendicular to each other. D orbitals begin on the third energy level. Okay, the 3D subshell first appears on energy level 3. And within the 3D subshell, the d orbitals, there's going to be 5 of them. And you can see in this picture, they've got complicated shapes, but 4 of them, this guy here, this guy here, this guy, and this guy, they all look like 4-leaf clovers in a way. And if you were to look very closely, you could distinguish how they're oriented to each other. And then there's this 5th d orbital, which is the oddball among those. It kind of looks to me like a p orbital with a donut around the middle. So electrons, again, when they're in these orbitals, they're flying around within that region of space that you can see pictured there. So let's go back to just recap. On energy level 1, okay, on energy level, I'm going to erase a mess here. Let's just be sure that we've got this down pat. So on energy level 1, there is the 1s subshell, and within the 1s subshell, there is one 1s orbital. On the second energy level, there's a 2s subshell. Within the 2s subshell, there's one 2s orbital. And now there's also a 2p subshell, and the 2p subshell has 3 2p orbitals within it. When you get to the third energy level, we now have the 3s subshell, a larger sphere, so there's one 3s orbital. We have the 3p subshell, so we have a larger set of 3 orbitals, just like we had on level 2, so 3 3p orbitals. And now we have 3D subshell, and the 3D subshell contains 5 orbitals. And you see a number pattern developing. The S subshell has 1 orbital all the time. The P subshell has 3 orbitals all the time. The D subshell, 5 orbitals all the time. And when you get to energy level 4, so n equals 4, now you'll have the 4s, the 4p, the 4d, and for the first time, the 4f subshell. The 4s subshell contains one 4s orbital. The 4p subshell contains 3 4p orbitals. The 4d subshell contains 5 4d orbitals. And the 4f subshell contains 7 4f orbitals. This is very complicated when you compare it to Bohr's model with very simple orbits. The reason, fundamentally, for switching from orbits to orbitals like this, despite the complexity, is to try to obey Heisenberg's uncertainty principle, which we saw in class. Heisenberg's principle, remember, said that you can't know both the position and the momentum of an electron. So in the new model of the atom, we're living with a high degree of uncertainty by saying electrons are somewhere within these three-dimensional regions of space, flying around somehow, somewhere, and we're not trying to be explicit about calculating their energies, their positions, their momentums. We're leaving room for uncertainty to obey Heisenberg's uncertainty principle. All right, so this slide is looking at the arrangement of orbitals and energy levels. So when a multi-electron atom, notice that something funny happens. The 1s sublevel is the lowest energy sublevel in a multi-electron atom, so atoms beyond hydrogen on the periodic table. But notice that where in the Bohr model, energy level 2 had any electron level 2 had the same energy. In a multi-electron atom, if you're in a 2s sublevel, you have less energy than electrons in a 2p sublevel. So 2s is lower energy than 2p. In energy level 3, 3s is lower than 3p. And then notice in this arrangement, 4s sublevel is next highest in energy, followed by the 3d sublevel. And then the 4p sublevel comes next. And of course, there's more sublevels beyond this. Now this is confusing, but it's very important we remember this sequence. And I'm going to show you in a moment an easy way to remember this sequence of energy levels. It's so important because of the Aufbau principle, which is something you've used ever since you started drawing Bohr diagrams in grade 11. When you fill orbitals, just like you filled orbits in the Bohr diagrams, you have to start at the lowest energy level and build up. That's the Aufbau principle. So if we're going to put electrons in atoms, we always fill the 1s sublevel, then we move on to the 2s sublevel, then to the 2p sublevel, to the 3s, the 3p, then the 4s, then the 3d, then the 4p, etc. So we have to obey the Aufbau principle, therefore we have to know this arrangement of energy levels. But again, I'm going to show you in a moment an easy way to remember that. Also, notice in this diagram that we've got, there are different numbers of boxes. I'm not sure if you've noticed that, but does it make sense to you? Remember that the 1s sublevel contained only one orbital. So in this diagram, there's one box. The 2s sublevel has one orbital, so there's one box. Excuse me, the 2p, the 3p, and the 4p sublevels have three orbitals in them, so there's three boxes in each of those sublevels. The D sublevel has 5 orbitals, so this diagram is actually faulty. There should be another box there. 1, 2, 3, 4, 5 orbitals are in the D subshell. Okay? Pauli's exclusion principle tells us that each of the orbitals, in this diagram, each of those boxes, can hold a maximum of 2 electrons with opposite spins. We're going to need to remember that in a few minutes when we get to orbital diagrams. I said it was easy to remember that arrangement of orbital energies because it turns out the periodic table itself is arranged in this order. The first of all, notice that we're going to split the table into what are called blocks. So we have the S block over here, which are the first 2 groups of the periodic table. Now in period 1, helium is over here, but it's actually part of the S block. So imagine helium fitting in this little space beside hydrogen, and now you've got the S block, those first 2 groups. The P block is this section over here on the periodic table. Okay? the D block, and notice the P block, if you count, there are 6 elements in each period within the P block. A D block is this transition metal section in the middle, and if you were to count, you would notice that there are 10 elements within each row of the D block. The F block is down here at the bottom, that section of the periodic table you don't really get to very often. It's called the rare earth section, or the lanthanide and the actinide series. That's called the F block. And notice S, P, D, and F, those are the same as the sub-level designations we had a few minutes ago. Now let's walk across the periodic table. If you start up at hydrogen, and remember that energy level diagram that we just saw on the previous slide, the first period you are filling the 1s subshell, hydrogen and helium. When you get to the second period, when you get to lithium and beryllium, you're filling the 2s subshell. Then as you keep going on your periodic table, if you had one in front of you while we're talking about this, that would be a good thing, so you could pause the video and grab a periodic table. So we're going to start walking from boron across to neon, and here we're filling the 2p subshell. After neon, we get to sodium and magnesium, and that's filling the 3s subshell. And then aluminum over to argon, we're filling the 3p subshell. And now notice back on that energy level diagram that we had a moment ago, after 3p came 4s, and after 4s, we, for the first time, enter the D block, and so that was the 3d subshell. Now notice something interesting. After that, we go back to 4p, but notice something interesting here. If you label the periods on the periodic table, 1, 2, 3, 4, 5, 6, and 7, notice that whenever you're in the S block within a period, or the P block within a period, the energy level is the same as the period number. So in period 1, you're in the 1s portion of the S block. In period 2, you're in the 2s or the 2p portion of the S and P blocks. In period 3, 3s and 3p. In period 4, 4s and 4p. And that goes all the way down for S and P. But notice, in period 4, after 4s, we enter the transition metals, which is the D block. But we weren't in the 4D sublevel there, we're in the 3D sublevel. So simply remember that the D sublevels are 1 energy level lower than the row number that you're in on the periodic table. So this 3D subshell is in period number 4. The 4D subshell is in period number 5 on the periodic table, etc. Now the F block first gets entered here after 6s. If you looked at atomic numbers, you'd see that element 56 is here, element 57 is here. So notice when the 6s has been filled, we go down here and start filling the 4f subshell. Then when we reach the end here of the 4f subshell, we go back to 5d over here and continue our way across this way. So notice then that the 4f subshell was filled after 6s. So the F block is 2 energy levels lower than the row number that you're in. When you're in row 7 of the periodic table, in the F block, you'll be in the 5f subshell. In row 7, in the D block, you're in the 6D subshell. In row 7, in the S and P blocks, they're in the 7s and the 7p energy or subshells. So I hope it's a little confusing, but I hope that makes sense. You can see within the periodic table those energy levels and sublevels. Let's start to put this together and write some electron configurations. An electron configuration is a way to show where the electrons are in an atom. So for hydrogen, which is right here on the periodic table, there's hydrogen. Notice it's in the 1s portion of the periodic table. And in fact, it's the first element in the 1s portion. Hydrogen has one electron, which means that electron is in the 1s subshell. That's the lowest energy subshell. And to show the one electron there, we just put a superscript like that. So that superscript means one electron is in the 1s subshell. And that's hydrogen's electron configuration. Helium has two electrons. And so it has two electrons in the 1s subshell. Now remember, Pauli's exclusion principle told us that each orbital holds a maximum of two electrons. So since the 1s subshell has only one orbital, it's now full. So no more electrons can go in the 1s subshell. And notice on the periodic table, there's only two elements within that subshell. 1s1 is hydrogen, 1s2 is helium. When you get to lithium, lithium is here on the periodic table, so it's the first element in the 2s block. So we're going to start by, just like we would in a Bohr diagram, we put two electrons in the first orbit. We're going to put the first two of lithium's three electrons in the 1s subshell. So we'd say 1s2. Lithium has one remaining electron, so we have to move to the 2s subshell to put that one electron there. So notice now when we say lithium 1s2 and 2s1, what we're saying is that there's two electrons in the 1s subshell, and there's one electron in the 2s subshell within lithium. Now notice a short way to get that. I've been trying to explain what the electron configuration is by thinking about the electrons. But notice if we look at the periodic table, we can get the electron configuration in a very simple way. Lithium is here on the periodic table. It's the first element in the 2s block. So what I'm going to do is walk from hydrogen. We're always going to start here at hydrogen and to walk our way across the periodic table until we hit lithium. So hydrogen to helium, that would mean 1s2. We've just walked through two elements in the 1s block, so 1s2. And then lithium, 2s, and because it's the first element in that portion of the table, 2s1. All right? Let's see if we can use that reasoning for oxygen. Oxygen is over here on the periodic table. It's in the 2p block. In fact, it's the fourth element within that block. So there's four elements, 1, 2, 3, 4, 5, 6, like that. And oxygen is the fourth element within that portion of the table. So to walk across from hydrogen to oxygen, hydrogen and helium is 1s2. We've just walked across to helium. And then 2s is the next section on the table, and there we'd have to walk through lithium and beryllium, so 2s2. And then 2p for the first time, we are entering the 2p section, and oxygen is the fourth element, so 2p4. And now interpreting it in terms of electrons, oxygen has 4 electrons in the 2p subshell, 2 electrons in the 2s subshell, and 2 electrons in the 1s subshell. Looking at it just from principal energy levels, oxygen has 6 electrons in energy level 2 and 2 electrons in energy level 1, which matches its Bohr diagram if you think about that. Iron, if you want to pause and see if you can do this yourself, iron is in the first row of the transition metals. It's over here, Fe. It's the 6th element in that portion of the table. So if you count it from scandium here over to iron, scandium is the first element, titanium the second, vanadium the third, etc. Iron is the 6th element in. So 1s2 We've walked from hydrogen to helium on the table. 2s2, you're at beryllium. 2p6, you're at neon, right? Neon over here on the table, 2p6. After 2p comes 3s, so 3s2. And then after 3s comes 3p, and there's 6 elements across the p block, so 3p6, and right now I'm at argon on the periodic table. And then 4s2 in the 4s block, we've reached 4s, we've reached calcium over here, Ca. And now we're about to enter the D block, and I remember that the D block's energy level is 1 lower than the row number I'm in. So instead of 4D, it's 3D, and iron is the sixth element in, so 3D6. And notice if you add up all of these superscripts, 6 plus 2 plus 6 plus 2 plus 6 plus 2 plus 2, you have to get the number of electrons in an iron atom, which would be 26, looking at a periodic table. All right, so those are introductions to electron configurations. Pause the video and see if you can try bromine and strontium yourself. So bromine is in period number 4 on the periodic table, and it's over here. It's the 5th element within the 4p subshell. So bromine would be 1s2, 2s2, 2p6. I'm at neon now. 3s2, 3p6. I'm at argon. 4s2. And now I'm entering the D block, which is 1 level lower than the row number, so 3D. And there's 10 elements there, so 3D10. And then we're back to 4p, and bromine is the 5th element, 4p5. Now some people get a little confused because they remember Pauli's exclusion principle told us that each orbital can hold only 2 electrons. If that's true, then why can we put 6 electrons in the p subshell? Why can we put 10 electrons in the d subshell? Why can there be 4p5 at the end? The answer, of course, is that s subshells, there's only 1 orbital. So within each s subshell, you'll never have more than 2 electrons. But within the p subshell, remember, there were 3 orbitals. And each of the orbitals holds 2 electrons, so p subshells can have up to 6 electrons in them. The d subshell, remember, has 5 orbitals. So 5 times 2 electrons each, the d subshell can have up to 10 electrons. The f subshell, if we ever get there, has 7 orbitals, and so 7 times 2, the f subshell can have up to 14 electrons. Strontium is down here in period 5. It's the 2nd element in that 5s section of the table. So 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, 4p6. We've just arrived at krypton, and so now 5s, and it's the 2nd element, so 5s2. There's the full electron configuration of strontium. Writing out full configurations is not that hard, but it is a little bit tedious. There is a shortcut. You can use the shortcut only when you're asked for what's called the noble gas abbreviated configuration. Let's take a look at aluminum. If we were to write aluminum's configuration, aluminum is here, the 1st element in the 3p section of the table, we would have to go through 1s2, 2s2, 2p6 on our way to aluminum. But notice that the last noble gas before we hit aluminum would be over here, neon. 1s2, 2s2, 2p6, that portion of aluminum's configuration is really neon. So what I'm going to say here, the noble gas abbreviated form, is simply that aluminum's configuration is the same as neon's, and now I'm going to add the extra piece after neon. So if we started at neon and we kept walking across to aluminum, we'd have to go through 3s2 and 3p1. So there's the abbreviated noble gas configuration for aluminum. You can try nickel if you'd like. Nickel is over here. It's the 8th element within the 3D portion of the table. So the last noble gas before nickel was argon over here. So nickel would be argon. And then after argon comes 4s2. And it was the 8th element within the 3D subshell, so 3d8. Rubidium is in period 5, and it's the first element within the 5s block. Let's see if you could do its abbreviated configuration. So krypton was the last noble gas before rubidium, so we would say krypton, square brackets, and then we would add simply 5s1. So those are the abbreviated noble gas configurations for various elements. There have to be exceptions to the rule. The Aufbau principle said start at the lowest energy level and build up, and that's what we've been doing. But there are two exceptions between hydrogen and krypton on the periodic table that we have to memorize. When you get past krypton into period 5, 6, and 7, it turns out there's more exceptions, but we're only going to need to know these two for our test and exam. If I asked you to write out the noble gas abbreviated form for krypton, you probably would have told me that it was argon, right? Chromium is the 4th element within the 3D subshell, so you would have said argon 4s2 3d4. If you asked for copper, you probably would have told me argon 4s2 3d9. Copper is the 9th element within the 3D subshell. However, it turns out that these are the wrong configurations. The same problem happens to both of these elements. Here we have 4s2, and here we have a 4s2. It turns out that for chromium and for copper, one of the 4s electrons turns out to be in the 3D subshell instead. So a 4s electron jumps to the 3D subshell. So the actual configuration for chromium, the one that you would give me on a test or exam, is argon, and instead of 4s2, 4s1. And instead of 3d4, 3d5. So a 4s electron jumps to the 3D subshell. Same thing happens for copper. Instead of argon 4s2, we get argon 4s1. And instead of 3d9, 3d10. So if you're asked for the configuration of chromium, this is what you would give me. If you were asked for the configuration of copper, this is what you'd give me. Those are the only two exceptions to the Aufbau principle that you need to know for our test and for our exam. All right, and that leads us to the new topic, the last item in this presentation. So orbital diagrams. An orbital diagram, we saw this when we looked at orbital energies. It represents the orbitals with boxes. And in this diagram, they actually label above each box 1s here, 1s, 2s, and over here they've got the actual 2px, 2py, 2pz, which if you remember, p orbitals are on the x, y, and z axes. I don't do that myself. I would just say 2p. Now in these examples, lithium, beryllium, boron, down to neon, we don't need more than these, but if you needed more, you would simply draw more boxes. So after 2p comes 3s, after 3s comes 3p, etc., and then 4s, etc. Notice whenever you draw an S subshell, you draw one box. If you draw the P subshell, you use 3 boxes. D subshell, you'd use 5 boxes, etc. Within each box, the electrons are represented as arrows, and the arrows are pointing up if the electron spins one way, and they're pointing down if the electron spins the other way. Remember, Pauli's exclusion principle said that orbitals can hold 2 electrons maximum, and those electrons have to have opposite spins. So if you're going to put 2 electrons in one box, in one orbital, they have to have opposite spins, so we point one up and one down to indicate that. So lithium has this electron configuration, 1s2, 2s1. If you were asked for its orbital diagram, you would draw this. You would draw a box with a label 1s, a box with a label 2s, and then you'd fill the 1s box, 1s2, with 2 arrows, and 2s1, 1 arrow. The one electron by itself, it doesn't really matter, but it's normally left pointing up until it has a partner, which then points down. Beryllium, 1s2, 2s2, so again, 2 boxes with the label 1s above and the label 2s above, and 1s2, so 2 arrows in the 1s box, one pointing up, one pointing down, 2s2, 2 arrows in the 2s block, one pointing up, one pointing down. Boron, we need the p sublevel, 2p1, so it has 2 electrons in the 1s orbital, 2 electrons in the 2s orbital, and over here in the 2p subshell, only 1 electron. It doesn't really matter which orbital you put it in. Normally we just put it in the first one and move across. Now when you get to carbon, there's a really important rule, a new rule that we have to look at. It's called Hunds Rule. And Hunds Rule says if you're filling electrons within a sublevel, so filling up a sublevel with electrons, as long as possible, keep those electrons unpaired. Don't put 2 electrons in one orbital within a subshell if there's another orbital in the same subshell that's empty. So keep them unpaired as long as possible. See how that works for carbon. Carbon, 1s2, 2s2, 2p2. So the first 2 electrons go in the 1s subshell, and there's nothing you can do about that. The next 2 electrons in the 2s subshell, no problem. The next 2 electrons go in the 2p subshell. But notice we have 3 boxes. Do we put the 2 electrons together in the same box, or do we keep them apart? Hunds Rule says keep them apart. Keep them unpaired as long as possible, so we put the electrons in neighboring boxes in 2 different orbitals. The reason for that is simple. These orbitals all have the same energy, all 3 of them, and the electrons repel each other. So if they can get apart from each other into neighboring orbitals, instead of being forced to pair up, they would prefer this. Nitrogen ends in 2p3, so when you look at the 2p subshell for nitrogen, all 3 electrons are in separate orbitals because we're obeying Hunds Rule. Oxygen has 4 electrons in the 2p subshell, so now 2 of them have to pair up. If I was filling them, I'd put 1 in each orbital, then go back and pair them up. Fluorine ends up with only 1 unpaired electron, and neon, no unpaired electrons. They're all paired up. let's finish with you trying a few of these yourself, and you draw orbital diagrams for silicon, chromium, and selenium. So silicon, thinking of its electron configuration, it's going to be 1s2, so I'll put 2 electrons, one pointing up, one pointing down, and then another box for 2s2, and then 2p, I'm going to need 3 boxes, and it's 2p6. So watch how I do this. I'm going to obey Hunds Rule. 1 electron, 2 electrons, 3 electrons, then 4, 5, 6. Always one pointing up, one pointing down for opposite spins. And then we got to go to 3s. So another box, 3s2, and then 3p2. So another set of 3 orbitals for 3p, and 3p2 we'll put 2 electrons side by side like that to obey Hunds Rule. Chromium, remember, was an exception to the Aufbau principle. 1s2, 2s2, 2p, 1, 2, 3, 4, 5, 6, 2p6, 3s2, 3p, we need a set of 3 boxes here, 3p, 1, 2, 3, 4, 5, 6, and now 4s. Remember that it's not 4s2 for chromium, it's only 4s1. And then comes 3d, and we're going to need 5 boxes here, 1, 2, 3, 4, 5, and this is a 3d subshell. And for chromium, where it would have been 3d4, it's now 3d5. So 1, 2, 3, 4, 5. It ends up with 6 unpaired electrons, 5 in the 3d subshell and 1 in the 4s subshell. Selenium is a bit of a nastier one. Selenium will be 1s, 2s, 2p, 3s, 3p, 4s, 3d, 1, 2, 3, 4, 5, and then 4p with 3 boxes. And now selenium ends in 4p4. Looking at its configuration on a periodic table, it will end in 4p4. So 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10. 1, 2, 3, 4, 5. Then pairing them up, 6, 7, 8, 9, 10. And now 4p4, 1, 2, 3, and then pairing them up. We're obeying Hunds Rule whenever we do that. So those are orbital diagrams for the elements. They communicate the same kind of information as an electron configuration, but in a picture form instead. So this was a little bit of a long video, but I hope it's a useful review of electron configurations, orbitals, orbital energy levels, and orbital diagrams.